It's Friday. Well, no, it's not Friday. It's Monday. It just feels like Friday. Right, it's Monday. I think it's Monday. It's kind of weird. It's like the last day of lectures, right? The plan today is not to tell you anything new about any physics. It's just to attempt to do a review of a semester's worth of physics. Like in one lecture, I have some idea for how to do this. It's an experiment. Let's see how it goes. Before that, just a few administrative things. So first, all of the lecture notes are now up to date on Canvas. Second, a few of you have told me that there was an issue with the solution sheet for midterm 2. I have fixed it, I believe. Please tell me if I failed. Number 3, maybe that should have been first. Exam results are available for midterm 4. There was a large curve. You can see the details on Canvas, but basically, especially long problem 2 about the tipping over or not box was difficult for folks. So we had a sizable curve for the midterm. Basically, people got an 18-point bump if you took the exam. What else? Right, before I forget, okay? So I'm going to talk about the final logistics in just a second, the final exam logistics. But before that, as you study for the final exam, and I'll give suggestions for how to do that in a moment, one of the things you might want is the opportunity to ask me questions. And what I want to say is you're going to have lots of opportunities to do this because I'm going to do an office hour every day this week. Okay, so there's going to be one every day, and I'm going to try to vary the times a little bit, but they're generally going to be in the mornings. I will later today post all the info about the rooms and so on, because a number of them are going to be in larger rooms and some are going to be in my office, and you just choose which you want to come to. Okay, so that's verbal logistics. So now let's get into like a really important thing, which is what's the structure of the final exam and where do you go? Okay, so first, I think I said this before, I can't remember, but the format is going to be 4 written problems and 10 multiple choice problems. So you're going to have basically, why is it saying a bit less than 2x? You're going to have twice the amount of stuff you have for a normal midterm, but you're going to have 3 times the time. Okay? So hopefully that reduces stress levels a little bit, and you can focus on just showing what you know. The time for the exam is May 9th from 6:30 to 9:30. I didn't choose this date or time, and I might suffer because I might be one of the proctors, we'll see. And then the location is Brunings Hall, 2 different rooms. Okay, so watch out. So basically we want to be able to have everybody spread out a little bit as they take the exam, so you're not crowding into each other. And so room 220 in Brunings Hall will be for folks whose last names start with letters A through K, and then room 230 is for last names that start with L through Z. Okay, I put this up on Canvas as well as an announcement. It's also in these slides. If you want to know where Brunings Hall is, I forget that I don't know. I used to know, but I forgot. But you can find it on the campus map or just Google it. Yes? Oh gosh, I should fix the grade estimator. This is it's a different format from that. I'm sorry, that's a grade estimate. The grade estimator is a hangover from a course import from a different version of this class, so I'm sorry about that. Let me try to fix that. Yeah. Yeah, so no part of the final is going to be dropped. I see a couple of questions, so one roughly in the middle of the room and then one in the back. So go ahead. Good. The question is, when is the lowest exam going to be dropped? So that's just going to happen automatically in the grade calculator. So during this week, just to tell you about the logistics from my side, I'm going to get the scores for the labs from the TAs. I'm going to put that into Canvas as an upload into our main Canvas page. Also, I'm going to import the trimens and process them so that if you were here for most of them, you just get full credit for assignments. And like in Canvas, it's already set up so that your lowest score out of the 4 midterms is dropped automatically, like in the grading setup. So it's not something I have to do separately. That part can be done automatically. So hopefully it shows you a good estimate of your grade, because the syllabus will be built into Canvas. So I hope it ends up not being confusing. And there's a question way in the back, and then I see another person in the middle. Yeah, go ahead. The question is, I think the question was, what is the final exam worth, like as a percentage of the class? Go ahead. Good. So, let me answer it in 2 different ways, because there's sort of 2 different things you're trying to get at with your question, I think. So one is, what is the, like whatever score you get some percentage on the final, like how does that fit into your course grade? So for that, you should look at the syllabus. I have the recollection that you should check. Don't trust me right now, it's really, I'm trying to remember. But I think the final is worth something like 24% of your grades. That sounds about right. Okay? So whatever score you get, that's how much it contributes. So now you could mean a different thing, and you probably do mean a different thing, which is like, how do we structure the points between the written problems and the short multiple choice problems? And that's as follows. So the long problems are 25 points each, okay? And then the multiple choice are 5 points each. So there's 4 of these, and there's 10 of those, and if you add this up, it should be 150, it should double a midterm. So hopefully that helps. Okay, that's the plan for the breakdowns. Yes, you had a question, go ahead. Good. So the way that that's handled is the following. So there is a section in Canvas, in the Canvas assignments area, which says just like your midterms, okay? And those contain the 2 midterms that didn't need to be curved and the 2 that did need to be curved as the curved grades. And then that's what we actually use for grading. There's a separate little area for the raw quizzes. Those are the ones that have to be curved, okay? The raw scores. Their weight in the grading is literally 0. So we don't count the raw score. Does that make sense? Yeah. Okay. So you're learning a lot about how Canvas works on the inside. So I'm sorry about that, but okay. Other questions? Were there other questions over here before I continue? No? Okay. Well, you can always prod me or come to office hours or whatever later. So how do you study for this thing? Okay. So the final exam is intended to be comprehensive. So it's not going to be focusing just on gravitation or something like that. So the best way to study that I know, okay, is to start with midterm 1. You have the exam file. It's in the files area of Canvas. You have a solution for it. Go look at the solution. Try taking exam 1 again, okay? And grade yourself. Okay, you have the solutions. And what you will discover is that much of it, I suspect, you will find very easy by now, because you've been using it secretly the entire time. And then, whatever you don't find easy, that's something to study by digging into the homework, for example. And then keep doing it for midterm 2, 3, and 4. And so basically, I would work sort of a little bit backwards that way. Start with midterm 1. I think you'll discover that builds confidence, and then go into the semester until you identify the parts that you are still confused about and try to get better at those parts. I think that will help. Okay. Before I get into an attempt to do a review, do you have any questions? Yes?
Will the final exam be curved now?
Good. The question is, will the final exam be curved? The short answer is no, unless there is some truly epic disaster in writing it, which I think is very unlikely. If we end up writing an accidentally difficult exam, which hasn't happened yet for the final, to be honest, in my time writing it. See, we have these grade boundaries that we committed to in advance as being like something that is, we're not going to do anything harsher than those. But if it turns out that the final exam is like dragging everybody down because we accidentally put a problem that's more appropriate for like fourth year physics students than first year physics students, which we're not gonna do. But if that happened by accident, we would just make the grade boundaries more generous. I think that would be more straightforward than trying to fiddle with curving for the final. Okay. Other questions? Yes? No. So the question was whether homework, whatever homework we're on now, 14 or something, or 13, whether it was intentional to do today. The answer is yes, because I wanted the last homework to be due on the last day of classes and not like in the middle of study period, because that would be awkward. I also intentionally put fewer problems on it than otherwise, yeah. Other questions? Yes, go ahead.
Throughout the week, what time do you
Yeah, it's a great question. It's going to be in the morning. I don't want to say more specifically because I haven't quite finalized all of them yet. And so morning means before noon. Like broadly speaking, each day is going to be sometime before noon. But exactly when, I'm still trying to pin down a couple of room availability concerns. And I'm hoping to resolve that basically later this afternoon after the lecture. Okay, and it's going to fluctuate throughout, depending on the day, because I'm fighting other people for space. So, other questions? Okay. If you have a hand up and I'm not calling on you, it's an accident, not on purpose. Okay. Okay, so look, there's a challenge here. Okay, so we've been learning about mechanics for like a semester. There's a sense in which it's totally impossible to review it in one lecture, right? So the best I can do is the following. First, I can make a list of like general topics we have discussed, okay? But this is not an exhaustive list, and each one of these things has subtopics to it. But just to remind you, like this is the kind of stuff that we've been doing. We talked about unit conversions, how things move in a straight line. Along the way, we have to deal with the fact that the world is three-dimensional, so we have to keep track of position and how it changes in three-dimensional space, so that's the vectors. Then we got into forces, free body diagrams, various types of energy, kinetic energy, potential energy, how kinetic energy changes, that's related to work. Eventually, we got into ideas about momentum. Momentum is conserved, and what is the center of mass? And that led us to talking also about the other kind of motion you could have, in addition to just motion in a line, motion if something is spinning, right? And then that brings us to ideas like torque, angular momentum, angular velocity, angular everything, and equilibrium. How do you know if something, how do you think about something actually being not in motion? If it's just kind of standing there, not moving and not rotating, okay? And then toward the end, in the last week and a half, we talked about what happens if things wiggle back and forth, and a little bit about gravity. So, okay, that's like the course in one slide, but this is not useful for study here. So the thought that I have is that I'm just going to pick 4 examples of problems that cover more or less the whole semester, and just go through as much of it as I can in the time that I have, let you ask me questions. If we don't cover everything, it's okay, it's all on the slides. And it's just a way of reviewing one more time, okay? And, well, I can't cover all these topics, so I just picked randomly, okay? So I'm gonna do one from each of the bolded topics if we get to it. All right. So here's an example of a problem. Again, it's all already on Canvas uploaded. If taking notes makes it easier for you to think, please do so. If you just listening makes it easier, then do that. Okay? So suppose you throw a ball with a velocity of 20 meters per second at an angle of 30 degrees. So, okay, you see a problem like that, you immediately draw a picture. 30 degrees, 20 meters per second, right? That's the first thing that you do. And not only that, you give a name to this thing, theta, and you give a name to that thing, call it v. And then 2 questions. What is the speed of the ball when it lands, and how long does it take to land? Okay? So what's the landing velocity, and what is the, yeah, just go for that. Okay. So, now I'm immediately putting up a whole bunch of stuff on the slide, okay? But I just want to say that there are two different ways of doing this first part, okay? So one of the ways is to say, okay, so we know that the acceleration is minus g if we take a coordinate system where this is up, and this is plus, and this is x, and this is y. Okay, so, and this is minus 9.8 meters per second squared. And then you could study the motion as a function of time in the x variables. And you could study the motion as a function of time in the y variables. Okay, and you could think about how long it takes to reach the top of the trajectory, and then it takes twice that time to fall back down. You could work through all of this, okay? So that would be the kinematics way of doing this, and there's nothing wrong with it. However, there's a faster way of doing it, which is to use energy considerations. Because what we know is that energy is conserved. So the initial energy is the kinetic energy plus the potential energy, initially. And the same thing is true at the very end. Except, well, they're equal to each other, but the potential energy initially is 0 because I'm choosing to call the starting location 0 height. And potential energy near the surface is mgh. So that part is 0. This part is a half mv squared. Okay? And the final energy is again 0 for the potential energy because you're landing back on the ground and it's on flat ground. And so this has to be a half mvf squared. This is the initial velocity. But these have to be equal. So you can see that that vi has to have the same magnitude as vf. You set them equal to each other, and whatever the initial speed was has to be the final speed. So this is the kind of thing where if you didn't know about energy, you would now go and suffer for a while and use kinematics formulas. But with energy, it's like that. Okay? It's like, if I knew you would notice you could use energy, this would be like a multiple choice problem. If I didn't, it would be like a slightly annoying long problem. You have to use kinematics. Questions, comments, confusion. Notice that the angle didn't matter. I did, like, at the intermediate stages of doing kinematics, it would matter a lot. You would discover it cancels at the end. Okay. Well, how long does it take to land? Well, okay, well that's tricky, okay, because like this energy stuff is not useful for that, because it doesn't have time in it. But now our formulas for the positions might be more useful, right? So now I'm looking at that. Let me just do it on the board, okay? So what about landing time? Okay, so how do we think about that? Well, so T landing is twice the time it takes to reach the peak. Does that make sense? You go up, and then you come down, but the thing looks symmetric around the peak, right? The flight looks like this. So it's basically doing the same thing on the way up as it's doing on the way down. So what we need to do is to figure out the time to reach the peak. So one way to think about that is to say, okay, so what is true about T peak? Well, the velocity in the y direction at the peak has to be 0. Because you're going up, you're moving up, 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 so your speed is positive in the y direction. But then at the peak, you stop for just a moment and you come back down. So it's 0 up there. So that means that Vy peak, which is 0, is equal to the initial y velocity plus the acceleration times time to reach the peak. You all see it? Okay, but so this is 0, this thing is minus g, and this thing, now the angle suddenly gets involved. Because you stare at this picture, you say to yourself, aha, I need this part. So that is v sine theta minus gt peak is equal to 0. This is a number, this is a number, this is a number. That's not a number yet, but it's about to be. You figure it out. You plug it there, you're done. Now, on the slide, I used yet another approach. On the slide, I said, look, you start at 0 for the y position, and you end at 0 for the y position. So that's the thing, you know what the acceleration is, it's minus g. So again, you go and figure out VIY, plug it there, solve the quadratic equation, you'll get the answer. It's an easy quadratic equation. But honestly, this is more painful than, well, I don't know, it depends. Different people have different views of what's painful. Somehow this is not the first thing I thought of just now. Okay. Multiple ways of doing every problem. Any questions about this? So, in case you're wondering, this is something that is like in between, it's like a mixture of midterm 1 stuff with midterm 3 stuff. So hopefully you're looking at this and you're like, oh, it's not so bad. And if you're worried about it, if it is bad, then this is stuff you should review, and you'll be okay. Okay. So, next example. Okay, so we have a uniform, like stick. I don't have any sticks. We have a uniform stick. Okay, it's initially at rest like this. The pivot point is my fingers on my right hand, and it is going to do this. Okay? And so, somebody could ask you, some evil person like your professor could ask, okay, so suppose it swings all the way down, eventually, well, it's going to keep going, but what is the angular velocity at the bottom? And also, what is the speed of the stick when it's at the bottom, and you ask about the speed of the very bottom of the stick right here? Like, how fast is that part moving when it's here? Okay, that's the next example. So let's work it. It's not so bad. Okay. So to do this problem, somebody would have to have told us the moment of inertia for a stick around its center of mass, which is that for a stick of length L and mass M. Assume that somebody gave you that on an exam. I'll make sure of that on the final. And then, well, let's see. In this problem, like my thought process is this. Nobody asked us anything about time information. There's no friction in the game. So the thing that comes to my mind is, can I use energy concepts to get what I want? If yes, that's going to be the easiest way. And then the other thing is, suppose you know omega, then we would know that V of the endpoint is omega L. Does that make any sense? That's one of our formulas. You can find it as a formula sheet. So the point is, the whole game is to get after omega. If we get omega, we automatically get the velocity of the endpoint. And since no time is being asked about it and there's no friction in the problem, hopefully energy can win the game for us. Okay? All right. So what can I do with this? Okay. So the first thing to notice is that if energy is conserved, which it will be, the change in gravitational potential energy, which is what's going to be happening here, the only reason the stick would like swing down is because of gravity, its potential energy due to gravity is going to change. All of that change has no choice but to go into kinetic energy. So let's think about that. So the change in gravitational potential energy is going to be mg, and then the change in height. But now the thing is that if you draw a picture, here's the stick. When it falls down like this and ends up over here, different parts of it have fallen down by different amounts. So change in height of what is the question. And the way to think about this is, this should be viewed as the change in height of the center of mass. You can get, that's how to think about these problems. So the center of mass, when it's at the bottom, is here, right? And this length is L over 2, and it used to be up there. So the change in height is L over 2. So the change in potential energy is mg L over 2. And that is all getting fed to kinetic energy. And now the other thing is this thing is rotating. So it's rotational kinetic energy that we're after. Okay, so the kinetic energy at the end, this is a half I omega squared, right? And the change in potential energy goes into kinetic energy. Okay? So now we need to know I. So we have I for the center of mass, but that's not how it's swinging. It's not swinging around this point, it's swinging around the end. So I around the end point is I around the center of mass plus m times the distance from the center of mass to the axis squared. That's the parallel axis theorem, which will appear on your formula sheet. And we've done this like many times for this particular thing, so I'm not going to do it in real time, but this is 1/3 ml squared. I've only memorized it because I'm teaching this class. In about 2 weeks, I will not remember this again until the next semester. And so, okay, we're almost there. So mg L over 2 is a half times a third times ml squared times omega squared. Okay, so what the heck is omega? So let me see if I can do it. This 2 cancels that 2. This L cancels the power 2 over there. And so the m cancels the m. Okay, let's see. So this is 3g over L is equal to omega squared. Okay, that actually passes a unit check for what it's worth. Because the units on one side are those of omega squared, which is 1 over seconds quantity squared. 1 over second squared. And the units over here are meters per second squared divided by meters. So again, 1 over second squared. So it passes the sanity check. Okay, so we got the answer, right? So we get that omega is that, and I mean, I'm not gonna bore you by showing you how to simplify this, but you don't have to, you just plug it in your calculators. If I have numbers in the problem. So we're set. Okay. Questions, comments, confusions? Yes, go ahead.
Why do we need Fermat's theorem?
Good, because the question is, why do we need the parallel access theorem? See, I assumed that your formula sheet had information about the moment of inertia around the center of mass. Here. But you can't use it directly in this problem because the stick is not rotating around the center of mass, which is there. It's rotating around the end point. So you gotta transfer this information into information about the moment of inertia around the point you're interested in. And that's what the parallel access theorem is for, and I used it right here. Does that help? Excellent. Other questions? Yes, go ahead.
Where did you get the 1/3
Oh, good. Great question. Where did I get the 1/3? The honest answer is I totally cheated. So let me show you. I cheated, but based on memory, but let me show it to you how it actually works. So this is 1/12 ml squared plus, from here, 1/4 ml squared. So far, is it okay? Okay. So now I gotta put these two things together. So this is 1/12 plus 1/4 ml squared. And now we have an exercise in combining fractions. So the way to do it is to say that if I multiply the top and bottom here by 3, I'll get 3/12 ml squared. And this plus that is 4/12, which reduces to 1/3. Okay? I only skipped the steps here because I've done this enough times this semester that I happen to have memorized this process, the end point of this process. But if you haven't, that's totally fine. You just do the steps. Other questions? Okay. Very good. So we just reviewed circular motion for the acceleration, right? Okay, so now, what about momentum conservation? Let's talk about that, okay? So imagine that I now chain together two problems. So the starting point is the one we just did, that's still on the board. But actually, when the stick swings down, there's a ball on the ground, and it smacks into the ball. And so, let's say the collision is elastic, and you want to know, what is the speed of the ball after it got smacked by the stick? Okay? So, and the main thing in dealing with this is just not to panic. So, see, the assumption is there's no friction, the ball isn't getting too squished or anything, everything is elastic. So what that means is that we should be able to use both energy and momentum conservation to figure this out. The bar itself is rotating, so we're going to need to take it, like angular momentum into account somehow. Now the ball is just moving along the ground, so naively that's not any kind of rotation, but let's see. Okay, I need to erase a couple of things, otherwise this is going to get confusing. Okay, so one thing that I haven't said, because this is like me just like sketching out some examples and not carefully writing an exam problem, I want you to assume that this ball slides without rolling. I now called it a ball. If you want to think about it as a block. So the idea is not to take into account rolling motion of the ball. That would just make it more complicated. That's not where I was headed here. Okay? So the way to think about it is this. First, we got to keep track of the energies. So we're going to have some initial energy, we're going to have some final energy, and we're going to say that since everything is elastic, we're going to say that the energies are equal. More precisely, we're going to have some kinetic energy and some final kinetic energy. So we're really going to say that the kinetic energies are equal before and after the collision. Roughly speaking, because just before the collision, just after the collision, gravity is not so important. The role of gravity was just to get the stick to be moving really fast. But after that, like the collision happens on the ground. And then the other thing is we're going to have an initial angular momentum and a final angular momentum, and they have to be equal. Okay, so I am using angular momentum here and not linear momentum because the stick is rotating. And so we're going to get very confused if we try to just use linear momentum. Okay. Well, so what do we need to do? So, okay. So the initial kinetic energy is whatever we had over there, right? So it is a half I omega bar squared initial. Does that make any sense? So like the ball isn't moving initially. The stick is moving with this kinetic energy. What else can we say? Oh yeah, well the initial angular momentum is I bar omega bar I. So this is the angular momentum of the bar. Does that make sense? The bar is the thing that's moving, it's rotating, so it's got an angular momentum. Okay. Now, for the kinetic energy, final, we are going to have a half I bar omega bar final. See, it's going to give some of its energy to the ball, so it's going to slow down. So that is not going to be equal to that. But then the ball also has some energy. 1/2 m ball v squared. And we're after this. This is what we want. This is the goal. Right? And then what about the final angular momentum? Well, everybody's moving in the same general direction, right? The stick and the ball. So what we can do is we can say that this is I bar omega bar F plus, and now this is the hardest part of the whole problem, what's the angular momentum of a ball, which is rolling on the ground? Well, that's mvl. Y'all remember this? If I have an axis and something is moving, then what you want to know is the distance from its straight line path along a perpendicular, like that. So this would be L, the size of the stick. And so you need to know the momentum of the ball, this is mv, times the stick's length. So there it is. Okay, so once you set it up, to be honest, this is it, okay? Because now, you set this thing equal to that thing, and this thing equal to that thing, and you know what this is because we just calculated it, somewhere over here. And then you, metaphorically speaking, turn the crank and do some algebra. So, okay. So I did some of this algebra privately, 2 equations, 2 unknowns, you solve it. Oh, I forgot to tell you what the answer was, I'm sorry. In case you're worried, if anything like that, 1 second, were to appear in an exam, this would come in many parts. You would have many chances to show you know what's going on before you're asked to actually solve the 2 equations. And if that's the last part that you somehow mess up, you're not going to lose that many points. Go ahead, questions?
In
That's a great question. So what you're saying is that we know the linear velocity of the endpoint, and so can't we just use linear momentum conservation to figure out what's going on? And the reason that we can't quite do that, okay, is that only tells us what the endpoint is doing. But the thing is the endpoint is rigidly connected to everything else. And so the thing that slows down after hitting the ball is not just the endpoint, but the whole rest of the stick. And that means knowing what the endpoint is doing is not enough for us to solve the problem using linear momentum conservation. It's because of, you see, if the endpoint, if the stick like hit the thing and somehow it broke, and all you have to keep track of was just the last little bit of the endpoint and the rest of the stick just kept moving and didn't care, then linear momentum conservation would have worked. But you can't do that because the stick keeps moving as a whole. You gotta keep track of that motion as a whole, which is rotational, which is why I brought in rotational angular momentum into the game. Does that make sense? Okay. Other questions? I have to say, I intentionally made this kind of hard. Not to terrify you, but hopefully to give you some idea that you can like put different things together. But also just to tell you, like, if we do that, we're going to try to, metaphorically speaking, hold your hand to the problem, break it down into many pieces, so that you hopefully don't get lost. And a big part of not getting lost here is not panicking and just staying organized. Okay. All right. So what about this? Okay, I have a last example. We haven't had any friction so far, right? And I don't remember if I have it here either. All right, well, fine. So, suppose you're driving in your car at 30 meters per second. I'm not sure what that is in American units, but maybe 60 miles an hour, I'm not sure. You know, you're on your phone, and you shouldn't be, but you are. We all know we are. We do that kind of thing sometimes. And when you look up, you see a T-Rex 100 meters ahead of you, as illustrated there, lifelike. And you definitely want to avoid hitting it, okay? And you either have to hit the brakes or turn. And let's say this is all happening in a parking lot, okay? So turning is totally fine, you're not going to hit anybody. And you want to minimize the forces involved on you. Because if you brake too hard or turn too hard, it's going to hurt. So what should you do? Okay, that's the problem. And again, this will be broken up into many pieces. I'm not expecting you to see this question and then like, go. If you finish taking physics 1302, I would expect you to be at that level by then, but maybe not yet. So what do you got to do? Well, okay, so basically, let me try to slow myself down a little bit by writing on the board. Okay, so we have two options, right? Stopping or turning. So you gotta treat them separately, compare and contrast later. Okay, so if we stop, there is going to be a force involved, which is equal to mass times acceleration on the person who's doing the stopping. And so how can we characterize the force? Well, we know, so like what do we know? We have a distance in the game, which is 100 meters, distance to the T-Rex. Let me stick to the same notation as in the slide. This is delta x. And we have an initial velocity, a final velocity, and we're trying to get the acceleration. If we know the acceleration, we get the force. So this is your final velocity squared, initial velocity squared, divided by twice the acceleration. Now, in this formula, the final velocity, if you're going to be stopping, is going to be 0. Your initial velocity is well, I'm just going to write it like this. divided by twice the acceleration. This is delta x. So from here, what you could do is you could solve for a. A goes over here, that goes over there. So a is in magnitude vi squared over 2 delta x. So the force is in magnitude that. So far so good? That's for stopping. This is where you see the T-Rex, you slam on the brakes, and you manage to stop right in front of the T-Rex. By the way, this is a terrible idea, right? I mean, this is not what you want. Yes, then you avoid hitting the T-Rex, but now you stopped at their feet. So, not a good idea. Okay, but now what about turning? Okay, now if you turn, you're going to experience some force as well. So there's going to be a centripetal force. So the picture would be, this is your initial position, this is the T-Rex, and then, so wait, what? 1 second. How do I draw this in a coherent way? No, this is, drawing is very hard. So bear with me. Very well, this is intended to be a bird's eye view. What I'm going for here is that I am thinking about doing the turn in such a way that the radius for the circle you're going to execute is the distance to the T-Rex. Okay, so roughly speaking, if you were, oh man, okay, I think I know what my problem is, which is not enough coffee, but nope. Okay, I am failing at drawing this in a coherent way. I'm sorry, it's a great way to end the semester, just as the way it's been going. But let's say that your radius is the distance to the T-Rex. Okay. So from here you can you just write down the answer. So this is mv squared over delta x, mv squared over r, and now you can compare to that. And you can see that this thing right here, this is the initial velocity, is twice that of the turning force. So you experience more force if you do it this way, but at least you're turning away from the T-Rex, which sounds better to me. Okay. So that's all I have to say about that. I'm basically out of material for the semester, okay? So I hope you have a good luck with the final. I hope you don't need any luck. If you have questions before the final, just email me. Come to office hours. I'll announce all of that. And you've been a great class. It's been